Hey guys, my name is Damien, and I've been working in the field of machine learning, deep learning for a while now. Um, I've worked in the field of self-driving cars. I've taught robots how to assemble car components. Right now, I'm working um, on the sparsification of neural networks. And in this tutorial, I would like to show you how to code the diffusion model from scratch. So many of you probably know right now the field of AI is pretty much overwhelmed by the new discoveries in the space of vision, where we are able to generate high resolution, high fidelity images. And this is due to the advances in the diffusion models, right? So stable diffusion is a very good example of a method which can really do astonishing things. But before we dive deeper into diffusion models, I would like to first talk about diffusion in the context of your, high school chemistry class. So what's diffusion? Diffusion is basically a movement of particles from high to low concentration, right? So if you put dye inside the water molecules, over time, the molecules of the dye will spread out and mix evenly with the water molecules. This is basically a second law of thermodynamics, right? That the entropy over time increases, and all the systems basically, have the impulse to go towards higher entropy. So basically, we have some particular structure at the time step t0, right, which gets destroyed over time. It diffuses. And this notion of diffusion is the driving idea here in the context of diffusion models. So the way so the goal is to teach the network to basically, given some training set, PX, to be able to autonomously on its own generate new novel image samples which look as if they were coming from this distribution PX, right? So how does the network learn this? It uses the diffusion process as a kind of like a proxy. So we have two diffusion processes. We have the forward diffusion process, which is fixed and does not involve the neural network. And we have the reverse or backward process, which is actually driven by the neural network, right? So in the forward diffusion process, what we do is we take a clean image and we gradually, over t time steps, apply Gaussian noise, right? So what we effectively do is we destroy the structure of the image in the same way that the dye diffuses in the water molecules. And then we ask our network to basically reverse this process, right? To repair the damaged structure. And by learning the denoising process, right? So the network over time learns, for example, to take this noisy image and remove the noise to get the original image, right? By learning this capability, the network can at some point just receive just a white noise, just a Gaussian noise, and from that infer what the clean image would look like. This is the idea, right? So as I have said, we have the forward process, which is going from x0, clean image, to xt, which is just noise. And this happens programmatically in t steps. Those steps follow the Markov chain. So the Markov chain is basically a set of transitions where every transition only depends on the previous one, right? So in case of the forward diffusion, our transition is just applying a Gaussian noise with some noise variance to the previous image, right, which can be noisy if we are not in the xt equal to 1. And this is, as I mentioned, there is no learning, no neural networks involved. This is just adding noise. But if you want to go backwards, we want to basically sample from distribution p xt minus 1 given xt. So given a noisy image, give me something less noisy. And this distribution is very hard to learn naively. So in machine learning world, there is this family of methods which fall under the umbrella term of variational inference, which basically their goal is to enable us, machine learning people, to learn very complex, very often intractable distributions by approximating them using simple distributions. For example, multidimensional Gaussians. And yes, Stable Diffusion does use variational inference. I will not go into details, but basically our goal is to find this distribution, right? So q xt minus 1. This is a simple transition, right? Applying Gaussian noise, but going backwards, going from noise to the structure, this is difficult, right? So this is why we employ neural networks to help us solve this problem. And this will be the reverse process will be actually learned by the neural network. And the funny thing is, what I'm going to show you is not very different from state of the art conceptually. I mean, the main reason why diffusion models are so powerful right now is that we have understood that we can do this diffusion not in the image space, not in the pixel space, but in some latent space, which basically gives us much more capabilities. Yes, so after you're done with this tutorial, I recommend you to read the paper Diffusion on latent diffusion, right? Yeah, this is the paper. And when you understand this paper, and it's a very, very cool read. It's not difficult, I would say. You will actually understand how are we now able to generate those incredible images that the whole world is right now talking about. Okay, 3 sources which I will be using for this tutorial. The great blog by Lillian Wang, where she describes the fundamentals behind diffusion models. One of the classical papers on the diffusion models. This is by any means the only paper, but this is the one which I read initially, and I very much like. I just like the paper. It does a very good job in explaining what's going on, and we'll be implementing those 2 algorithms. And I also recommend you to read the kind of like a summary, a wrap-up, a review of the basics of diffusion models. I think for visual domain, yeah. So it's like a nice summary of what has happened over the past several years in a nutshell, and this paper very well lays out the technical fundamentals behind diffusion models. All right, so yeah, let's do some coding. First thing we're going to do, we're going to implement the forward diffusion. So forward diffusion process is basically a Markov chain where we start with the clean image without any noise, and then we gradually apply more noise, so at the end we get a fully noisy image, just a pure noise, pure isotropic Gaussian distribution. So how we go from a step to step is basically adding more noise to the previous step, right? So getting from xt minus 1 to xt is basically sampling from the Gaussian distribution with the mean multiplied by this factor, 1 minus beta. And then we also increase our variance by the factor beta of t, right? So basically, what beta is basically the amount of noise that we want to inject at this transition, right? So the bigger the beta, the smaller, so the mean is going to shift from its original mean to basically 0. This is the idea, right? Like if the beta is very small, this whole thing is going to be also very small. Makes sense, right? So we basically go from the original image to something which is going to be a Gaussian of the mean 0 and unit variance. Yes, so here the authors of the paper use a very smart trick. So we know how to get from less noisy image to a more noisy image, right? This is how. This is the equation. Basically a Markov chain. But we can also have a closed form solution for getting from x0, our original image, right, from x0 to any state, to any degree of noisiness in one pass. I mean, like, we don't have to compute x t minus 1 to get x of t. We can directly go from x0 to x of t. We can basically, how we can do this, we can basically rewrite x of t in terms of any previous state, right? And if we do it, several times, we can see a pattern, and we can actually define a very nice closed form expression for x of t, which only depends on the initial image, right? So this is the thing which actually governs our forward diffusion process. This is the thing which we want to really implement. So let's get to it. Let's do some coding. Cool. So we have our clean slate. So let's first say what we need to implement. We want to get this thing, right? So we want to get our new mean. Our mean will basically square root of a hat of t times x0 and our variance. Our variance will be, now watch out, this is standard deviation, so we actually need to have the square root of that, which is 1 minus alpha hat t, and then that's it. Then we just multiply this by the random noise, and this is basically this is how you implement going from x0, from the clean image, our input image, to any given time step t in our Markov chain. Okay, cool. So let's get to it. Let's import torch. And first, let's define our x0. It's going to be an image. Actually, it's going to be just a random random tensor. Let's say it will be batch size 2, 3 channels, and 32 by 32. So like a like a dummy image, basically. And now we also, let's define our betas, right? Let's define our variance schedule, right? So let's say that our betas are, it's basically like a 1D vector, and we go from 0.5 to 0.1, 0.15, 0.2, 0.25, right? Just a dummy linear schedule. And also we can specify our time steps. Let's say, for example, that we want to get a x of t at time step 1 and time step 3, right? So t is torch tensor at 1 and at 3. What's important is that that the batch sizes of x0 and t is the same, right? So basically x0 is, those are 2 images, right? And we also want t to have the same batch size as x0. Okay, cool. Now, we want to get the value a hat t, right? So as we have said before, beta or betas are, let's say, amounts of noise that are being applied at every time step of the diffusion process. Alphas are actually 1 minus betas, so it's amount of original images information that is being preserved after a diffusion process step. So alphas are actually 1 minus betas, right? This is how we define alphas. And what's alpha hat? Alpha hat is basically a summation of the t first alphas. So alpha hat of t is alpha 1 times alpha 2 times ... times alpha t, right? So it's a cumulative product, which is very easy to get in PyTorch. So alpha hat is just a torch comprod of alphas axis 0. Right? We can verify if our alphas is this, then our alpha hat will be, this will be rewritten. This value is the 0th value of alphas times the first value of alphas, and then the second value of alpha hat are those 3 multiplied, right? So it's a cumulative product. What else do we need? Okay, now we need to do one additional step. Let's take a look at the shapes of alphas and x0, right? So alpha hat it's a vector of 5 values. It's a tensor with 5 values. But at some point we're gonna be adding the information from alpha hat or multiplying information from alpha hat with our x0. And our x0 is its size is different, right? So we need to have a way how to extract the information from alpha hat and also be able to then multiply this information with x0. So what we do is, first of all, as shown here, we need to extract from alpha hat the alpha hat value which corresponds to the given time step, right? So for example, alpha hat contains those values, and we want to only fetch those which correspond to the specified time step. So we want to get the first alpha hat value and the third alpha hat value. So what we're gonna do is we're gonna use our gather function, which actually we should call this on alpha hat. Alpha hat gather axis. We're gonna use the default axis, the first one, and we're gonna use the t vector. So basically what gather does is it will, from alpha hat, it will pick those values which are specified by t. So t here is being acts as an index, like a list of indices, and given those indices, we're gonna pluck out the values from alpha hat. Okay. Oh yeah. T axis minus 1. Well, let's take a look. Alpha hat gather. Why doesn't it? All right. Right, let's just verify it. Yes, so we want to get the first value and the third value, and this is what we get, right? Perfect. All right. This is great. Now, what we also need to do additionally, so right now we have a result, which is of size 2, same as our batch size. And now what we all need to do is we need to reshape it so it has 4 dimensions. I mean, it has the number of dimension is 4. Cool. And now we'll be able to basically multiply what's this value by our original input image, right? So at this point we can already say, you know, mean is equal to result squared times x0, and variance will be equal to square root of 1 minus alpha hat t, result, times random noise. And what is noise? Noise will be basically a tensor of the same shape as our x0, but the values in this tensor will be basically sampled from the Gaussian distribution with the mean 0 and standard deviation of 1, which is torch rand like this guy, x0. Let me take a look. Fine, okay. So our x of t will be mean plus variance. And x of t will be, it's actually 2 images, as we have said here, 2 images, 1 image. at the time step t with less noise, and one image at time step 3 with more noise. All right, so xt is 2 images, first one and the second one. So I'll clean up this code. I'll actually create a function out of it, and then we can test this function on a real input. Okay, so I've cleaned up the code. We have our forward diffusion function. So basically, I took all the everything I showed you before, and just made it a bit more neat. Yes, so let's test this function on a real input. So I have here a URL. It's an image of a raccoon, and I will download this and save it onto disk. Oh yeah, of course, we need to do some imports. urlib. I may as well already import image. All right. And now let me open this image. Okay, fine. So that's our test image. As you can see, it's a raccoon. So what we would do first, this is a pill image, right? So we need a transformation which will take this image from pill to PyTorch tensor, right? So we can import Torch Vision, or we can just import transformations. Transforms. Yeah. So our transform will include, so this one goes from pill to torch. So this image will first needs to be resized. So we say transforms, resize, and we're just going to be operating on the on the same 32 by 32. Sounds good to me. So first we resize, then we actually convert this to a PyTorch tensor, and finally we do the one small smart trick. We will be adding noise to this image, right? And the noise comes from isotropic Gaussian distribution. So it's going to be sampled with the mean of 0 and some standard deviation, right? So the pixel value of this noise, well, there will be, centered around 0, but there will be negative and positive. So our image, by default, at this point, would be scaled from 0 to 1. This is how Torch does it. So what we need to do is we actually need to have some transformation, which will scale it from -1 to 1, right? So the noise and the image, they have the same, the pixel values live in the same range, right? The domain is the same. as you'd like. So we're going to use a lambda transform which will do the following. First, we'll multiply every pixel value by 2, and then we'll subtract 1. So this will map the two extreme values, 0 and 1, to 0 will become, this is going to be 0 minus 1, so 0 will be minus 1. And then 1, another extreme value, will be 1 times 2 minus 1. So 1 will map to 1, right? So this way we have transformed our pixel values from the range 0 to 1 to minus 1 and 1, just as we have expected to do. And maybe just for the fun of it, let's define a reverse transform, which will take us back. So from torch to pill. So we'll just reverse the whole process, right? So we'll say transforms lambda t. First we add 1 and then we divide by 2, right? Then what we need to do is we need to do t permute. So here we need to, by convention in PyTorch, the channel dimension of images follows the batch size. It's not the last dimension, it's the second one. It's not so the first one is batch size, then it's channels, and then it's height and width, right? This is the torch convention. In NumPy, the channel dimension is the last one, right? The fourth one. First we have batch size and height and width, and then channels. So here we need to basically make sure that the channel dimension is not on the first place, following the batch size, but it's at the end, right? So we're just gonna say permute 1 to 0, right? So there's no batch size here in this case, right? So you basically say the 0th dimension, which is channels, it needs to go at the end. So effectively, we go from channels height width to height width channel. Height width channel here. Cool. Then we need to multiply every pixel value by 255, right? To be in the valid range for NumPy or pill. And lastly, we need to go from torch tensor to a NumPy array, and then actually want to change the type to unassigned integer. And finally, to pill. Looking good, right? So we have one transformation, which takes us from the pill image to the torch tensor, in the form in which we are actually going to feed the images to the network. And we also have the transformation of this image from PyTorch to pill. We're going to use it mainly for plotting, right? To basically see what's going on with our image as we add noise, for example. Cool, exciting. So the torch image is transform image. Oh, all right, a couple of bugs to fix quickly. so our torch image looks good. And now let's plot what we have computed. Show, reverse transform, torch image. Oh yeah, nice, right? So what we have done with the original image, we have resized it to 32 by 32, and that's it. All the other transformations here are being undone by this function, but this is basically how our input to the network looks like. Okay, and now the fun part. We can say the following thing. Diffusion model. Oh, we don't have a model. So right now we have a forward diffusion function. So what we can do is we can say, okay, our betas, right? It's a linear schedule with 5 values, right? So our Markov chain has 5 time steps. So for every time step, let's see how the image will look like when we add, how the image looks like when we progressively add more noise, right? So we can say that T is equal to torch tensor 0, 1, 2, 3, 4, 5, I reckon. And now we can say noisy images. So what we do here is actually we perform the forward diffusion. We say forward diffusion, and now x0 is our torch image. T is T. What's going on? All right. One thing that we need to do. Okay, for now, let's say that our batch of images is torch stack. Torch image times 5. So we're gonna give the function batch of 5 images, and then also a batch of 5 t values. Okay. Those are our noisy images, and now we can actually plot them. So for image and noisy images, plot im show image flat show. Oh, right. Yeah. The forward diffusion function returns the xt, but also returns noise. So it returns a tuple of objects. This will be important later on. So right now we can just say the noisy images, and then nothing is returned by the forward diffusion. Oh yeah. What's going on? Okay, looking good. Looking good. Result squared. Oh, got it. Now, we are missing our reverse transform function. All right. So this is how it goes. We have our image at time step 0, right? So this is a original image that has not been altered. And then we apply gradually more and more noise to this image, and thus we basically destroy the structure of the image. This is actually how we're going to generate, the data for the network, for the stable, for the diffusion model to train on, right? So that's it for now. I will clean up the code, and in the next part, I will basically show you how can you start training a diffusion model. All right, so I have cleaned up the code a bit. So this is the current state. Some imports. So far I'm working on the CPU. The function to get the raccoon image. I actually create a class diffusion model, and one of the methods here is forward, which is the forward diffusion, the function which implements the forward diffusion. Also, I have my two transforms here, and I have a nicer implementation of this small visual I've shown you last time, where we basically show the initial image, a clean one, and then we display it once again, but right now with the noise added to it, right? So this is just a cleaned up version of what I have presented last time. So right now we're gonna implement the training routine, the training of the neural network. But first, let's think of what we really want to have here. So the thing is that we want to learn the structure of our dataset, right? So the forward diffusion basically allows the network. It's basically destroying the data, right? So the network can learn to undo the destruction. And by undoing the destruction, by actually adding a structure to noise, because the network will, how the network generates the images, right? It basically takes a noisy image, it takes noise, it takes chaos, it takes entropy, and basically adds a structure to a noise, right? So this is what we are training, a function basically which can create structure from noise, and this network will basically be a UNet, right? So the U-shaped network which takes image as an input, downsamples the image, and then upsamples it. So it takes an image, downsamples, upsamples, and then it gives you something, right? So in this case, the UNet will take the noisy image and will learn to output the noise, right? And this ability to extract the noise from the noisy image will be useful for the backward diffusion process, which will actually go from pure noise to structure, in opposition to the forward process, which we have seen, which goes from structure to entropy to noise, right? So to reiterate, we want to teach the network to take a noisy image and then extract the noise, just the noise from the image, right? And this is going to be used for, this is being used in diffusion models to basically generate images which look great to us, which have structure, but this is how they learn to do it, by basically by being able to capture the distribution, the PX, the distribution of the inputs, the distribution of images, exactly by learning how to go from noise, chaos, entropy to a meaningful distribution of structure. Okay, so the way how we do it, we can take a look at the paper. The training is fairly simple. So first, what we do is we sample so from all the images in our data set, right? We sample a mini batch of images. Then from all the possible time steps in our Markov chain, we basically sample some random time steps, right? So we can have a bit noisy image at time step 20 or super noisy image at time step 200. Then we sample the random noise, right? And we have seen this equation before, right? This equation is the forward diffusion. This is something which we have implemented last time, right? So basically, what we do is we have our network parameterized by theta, which takes the noisy input, outputs noise, and then minimizes the noise with respect to the ground truth noise, right? So it's basically this is basically a mean square loss between the ground truth noise, the real noise which has been applied to the image, and the noise predicted by the network. Yeah, so we're going to basically be implementing this. So let's get started. The UNet. Right now, the UNet, the architecture of the UNet is not in the scope of this tutorial. But you can trust me, this UNet is nothing serious, nothing fancy. There are some blows and whistles there, which enable the training of a diffusion model. But I'd rather talk about it in some, I would say, addendum to this video, and not really talk about this right now, because this is nothing really special. So let's treat right now this UNet as a black box, okay? Okay, fine. So UNet is the UNet. We're going to train. So first, what we're going to do something which is very characteristic when we want to kick off with the new project. We will overtrain on one batch of data just to see whether our network works properly. Like if the networks fail to solve a very simple problem, then probably we should not advance and give it more difficult task. We should go back to square one. We should go back to the drawing board and revisit our assumptions, revisit our architecture, because something must have gone wrong if we cannot solve a very simple task. Right? So what we're going to do is we're going to let's specify the hyperparameters. So we're going to train for, let's say, 100 epochs. Our print frequency is 10. So how often are we gonna print the training status, training progress? Our learning rate, 0.01, I think is fair. And then batch size, 128. Okay, cool. An optimizer just a simple Adam. Okay. So our for epoch in the number of epochs, well, we want to do the following thing here. We want first to say, so as mentioned here, our forward step returns x of t, right? Noisy sample plus the noise, the ground truth noise, right? So we can say noisy image ground truth noise equals diffusion model forward x0 t t will be sampled uniformly from diffusion from the number of possible diffusion steps. X0 is our input batch. And then given all those information right now, we can employ our UNet to predict noise from the noisy image, of course, given time t. The network has to know in which time step this image has been created, because the higher the t, the more noise has been injected. The network needs to know this, and then basically, change the weights of the UNet such that you minimize the L2 noise between predicted noise and the ground truth noise. This is roughly the pseudocode which we're going to employ here. Okay, so first let's create a batch size that we want to overtrain on. So batch size is 128. So right now let's just say torch stack torch image times batch size. Maybe for now let's set number of epochs to 1. Looking good. Our t will be a random integer from the range between 0, maximal number of time steps, which is defined in our diffusion model, here, time steps. So by default we have 300 time steps. And this tensor actually needs to have the batch size, right? And this needs to be a long, so this is an integer. We're just saving this t as integer and not as a float value, for instance. Okay, cool. So we have this, we have this. Now we can create our noisy image and ground truth noise by employing the forward model. T, and then predicted noise is UNet of batch size and T, sorry, noisy image and T. Yeah, and now, you know, rudimentary optimization code. So first we need to zero out all the gradients. Then we need to compute the loss. Okay, this comes from my UNet. Let me quickly fix this and I'll come back to you. Okay, so we can compute the loss between the ground truth noise and the predicted noise. And maybe just for fun, we can track the MSE loss per epoch. And then we need to do the backprop. And finally, this is how we end. This is our gradient step. Fine, okay. And maybe let's just make it run. Of times. Okay, so now we can probably also say if epoch is divisible by print frequency, we can first of all plot noise prediction between, you know, the ground truth noise and the predicted noise. So let's just take the first noise from every batch. It's going to be pretty interesting to see. I'll explain in a second. And then also plot noise distribution. To deal quickly with those bugs in the helper functions, this is what happens usually when you just paste the code. But I also decided that to migrate to a machine where I have access to the GPU, right? So this is my GPU device, Why? Not to waste time, basically, when I'm training, and it's pretty important because I want to really overfit to this one batch, to my raccoon batch. I really want to overfit hard because if I do, I'll be able to generate, new images. And of course, right now my expectation is if I overfit to one image of a raccoon, my network will consistently generate this image of a raccoon from the noise, because this is the whole distribution that it has ever learned. So let's rerun the whole notebook. And actually, let's see those helper functions which I have implemented. Of course, we need to first run them. Yes. So there are two helper functions. One helper function shows side to side the ground truth noise and predicted noise. So right now, as you can see, early on in the training, the predicted noise is very far off from the ground truth. This can be also seen here. So our ground truth distribution, it's a Gaussian, isotropic Gaussian, right? And we would like the predicted noise to mimic this distribution, right? Right now, the orange predicted noise distribution is, does not overlap with the blue one, because those values come from the initial initialization of weights. But over time, as you can see here, bam, the predicted noise and the ground truth noise, they start to really overlap, which means that networks is learning the structure which it has seen in the training set. And the same goes for the noise. You can see that the pixel values are very much the same in the predicted noise and in the ground truth noise. So we are on the right track. I will keep the network training for more epochs, and then we'll see whether we can also implement backward process and start generating images. This is the goal of the diffusion models. We are done overfitting to our single batch. So now let's get to the backward process, which is actually image generation from noise. So before I start, I should probably talk about the theory. So the forward process was going from clean image to the noisy one, destroying the structure. The backward process goes from noise to a clean image, from chaos to structure. Now, the derivation of the backward process is pretty complex. It basically involves, reversing the formulation of the forward process using the base rule. But because it's pretty, it's not difficult, it's just mathematically involved, I'll skip the derivation and just go to the pseudocode. So we were implementing the training before. Right now we'll implement sampling. So we go backwards, right? So first we sample pure noise, and then we're going to have a for loop where we iterate backwards over the diffusion steps, right? So if our forward process involved 10 diffusion steps, here we're going to go from the 10th to the 0th, right? So we're going to go 10, 9, 8, and so on and so on. So at every diffusion step, we will sample some noise. This is the noise for the variance. If we are at the last time step, right, we are expecting to get a clean image. We will not add any noise, but otherwise will basically sample the noise and will generate our new image, xt-1, so a bit more, a bit cleaner image, right, in this iteration, by taking the old one and basically, we just substitute the previous image, xt, in this equation. As I mentioned, this equation comes from the Bayesian theorem applied to our problem. Looks a bit more involved. It is not. One important thing to notice is here we have our network parameterized by weights theta, which takes as input xt and t. Also, this standard deviation or variance, this can take different values. For the sake of this tutorial, I took the simplest one, which is just beta at t, and it works for me very well. So yeah, this is what happens. You just go backwards. When it comes to the derivation, I took the liberty of implementing this directly in our model here, backward. I very much followed the same recipe as with forward, with the forward method. So I not want to repeat the whole coding process. I think it's pretty self-explanatory here. As I mentioned, my posterior variance t, which is this value, is just beta, so we're fine. Pretty simple. If t is equal to 0, we just return the mean. Otherwise, we remove the noise, basically. And of course, this method needs a decorator, torch no grad, which basically disables collection of possible gradients. We'll not do any backprop here, and it's possible that computing n steps where n is equal to 300 in our case, this can be just heavy for your memory, right? Because the PyTorch will store all those gradients from this gradient tree in your memory. So this can, not a good idea. Okay. So what we can do now is say, so we start from the noise, right? So we just say image equals torch random noise, and this would be one batch, three channels, 32. Oh, we should also reinitialize our diffusion model. Perfect. Yeah, and now for I in reversed range of diffusion model time steps, right? We're basically going to go from 300 down to 0. So for every I, what we do is we create our tensor T, which is just a tensor with one T value. I mean, in other words, we cast our I variable into T tensor. And then we just say, image. So this is our X at 300. This is our X at 299, at 288. Sorry, 298. So this is the variable which we're going to change in this for loop. Diffusion model, backward. Image, and then T, and then UNet. How do we call this? UNet in eval mode. Yeah, pretty much. And then we can say, you know, it will be cool to see how this noise gets removed at every time steps, but we don't want to, you know, print 300 images each for every time step. So let's just print the last 10. So if I is smaller than 15, plot imshow reverse transform, right? Image 0, plot show. Something is not properly. This is correct, but I think it will be even cooler to do this. Right? So that's our noise at time step 240. This is our noise at time step 180, 120, 60, and then 0, right? So this is the proof, the evidence that we have implemented the forward and backward process correctly, because from the pure noise we get the the mode of the distribution. I mean, we have only one image in our dataset here, but we get it correctly, right? So I think at this point, I will finish this part. The next part would be basically training the UNet on the ImageNet, sorry, not ImageNet, on the CIFAR 10 dataset. And seeing whether we can also, you know, notice something interesting, maybe play around with the capabilities of the diffusion model. All right, so I took the code that we have seen before, and right now I applied the model, the training process, the diffusion model to a bigger data set, to CIFAR 10. So CIFAR 10 is an image classification data set which contains 10 classes: cat, dog, deer, truck, ship, etc. So right now I set up my hyperparameters here. So the learning rate remains at 0.001. I train for 100 epochs with a pretty big, large batch size. I also invoke the training loader and the test loader. And here I basically rewrote the training routine. I copied the training routine from our previous part, right? So in this part, we do the training. Here we do the testing. One important thing is just for just for fun, I've added the capability of the network to also take labels as inputs. So right now, I was hoping for a network to learn how to generate images conditioned on the class label. Um, Nothing fancy in there. There is no attention module. There is no group norm. It's just very basic embedding of the label into some latent space, and then concatenating this latent space with the input. So this is what we have here. As we've seen before, we uniformly sample from the uniform distribution, our time step t. We run our forward diffusion process to get a noisy batch and noise, and then we predict the noise using the UNet conditioned on the class label, right? Here, this is where the backpropagation happens, and here we just have our validation run. So I've trained for roughly 90 epochs. To spare you the waiting time, I saved those models, and I chose to take a look at the one saved at epoch 80. I like this guy the most visually when it comes to the results. Yeah, so here I basically have a grid with the generated images by my network. So what I do here is basically for every class, and just to remind you, we have 10 classes in CIFAR 10, I display 5 images, right? So what happens here is for every class, our network generates an image from noise. So this is basically the showcase of what the network has learned using our code. As you can see, the results are not fabulous, but I think that it still proves that even though our UNet, the architecture has not been adapted a lot to handle conditioning. First of all, we can see that the network learns the distribution of CIFAR 10 pretty well. I mean, those samples, they do like real images from CIFAR 10, but also the conditioning, it's not too shabby, I would say. So if we take a look at the plane class, okay, this could be a plane, I think. Also the car, this looks like a car to me, pretty much. This guy as well. The birds, I can see a bird here. I can see a bird on a tree branch here, so pretty well. Okay, cats are a bit weird, but still, the images does look they do look the same. The shades of gray dominate those images, which looks good. Deer, same, green background, very characteristic for the deer class. I could see a deer here, for example. Okay, dogs are rubbish, frogs are also a bit weird, but horses, I mean, I can see a horse here, I can see a horse here, definitely. Ships, I can see a ship here, I can see a ship here, and trucks. Well, this is a truck, obviously. Yes, so all in all, in this tutorial, I've shown you how to, from scratch, how to implement a simple diffusion model, which is able to generate new images given a training set distribution, and also has some notion of label conditioning. Yeah, I hope it was useful. See you next time. And finally, as I promised, I will just speak briefly about the UNet. So don't get me wrong, this architecture is not really tweaked a lot. This is basically a generic UNet. that borrows from the ResNet architecture, right? So it's an hourglass network, which first takes an image, downsamples it, down to the bottleneck, and after the bottleneck, it upsamples the image, right? So this is the actual UNet class. So what happens here is we have our image input, our time indices, and you could also pass here labels if you decide to condition on the class labels. And what happens here is first we have a process of downsampling. And just to remind you, since this is based on the ResNet 50, we also have this notion of adding the residuals to the output of the convolution after downsampling, after every downsampling step. And conversely, after we hit the bottleneck, we start to upsample, right? Our block is also pretty generic. The only thing that happens is we do condition on two things, right? So our X here is a feature map, which is derived from the input image. We process it using convolutional layer, nonlinearity, batch norm, but then we also add a embedding, which is derived from our time index, right? So our time index is being embedded using the sinusoidal position embeddings. This is a method known from the transformers paper. Attention is all you need. And this is basically a pretty clever method to basically encode the notion of order in the network, right? So in a similar fashion as in transformers, we do it here. In transformers, basically the input sequence, for example, the sentence to the transformer, it was never a list, right? It was always a set. There was no notion of order between those tokens. So the sinusoidal position embeddings in that paper was basically telling us, about the order of those tokens. It was like auxiliary information. And similarly, in this implementation, we use those embeddings to also tell the network to encode this notion that if t is at time step 0, this is before t at time step 1, and this is before the t at time step 2, right? So we use those sinusoidal position embeddings to basically inject the notion of order, of some temporal dependency. And then we concatenate the information from the feature maps of the image with the information from the time steps embedding. And if we have labels, we can also do similar thing. We can basically map our labeled information into some latent space and add it or concatenate it with our information so far, right?